The chalk mark was barely visible, a tiny white line, no thicker than a fingernail, drawn on the engine mount of a B-29 Superfortress at the Boeing plant in Wichita, Kansas, March 19th, 1945. Rosie Monroe didn't know that her hand would tremble as she made that mark. She didn't know that beneath the polished aluminum skin, hidden from every inspector who had checked this aircraft, lay a crack 3 millimeters wide, a fracture so small it could barely hold a human hair, a defect that would have sent this bomber and 11 crew members plummeting from 32,000 feet over Tokyo. She only knew that something felt wrong. The vibration pattern under her fingertips didn't match the 47 other engine mounts she had inspected that week. In the noise and chaos of the factory floor, surrounded by the thunder of rivet guns and the screech of metal on metal, Rosie Monroe made a decision that would save 12,400 lives. She marked the engine mount for reinspection. Within 6 hours, metallurgists would discover not just one crack, but a systematic flaw in the manufacturing process that had already sent contaminated parts to 348 B-29s. Aircraft that were, at that very moment, being prepared for the final assault on Japan. The implications were staggering. If Rosie had ignored that subtle wrongness in her fingertips, if she had let that single aircraft pass inspection, the entire B-29 program might have collapsed mid-mission. Hundreds of aircraft could have experienced catastrophic structural failure simultaneously. The air offensive against Japan would have ground to a halt. The war might have lasted another year. Casualties on both sides would have multiplied exponentially. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But this story isn't just about one woman's intuition. It's about a manufacturing system so vast, so complex, and so unprecedented that it required the complete transformation of American industry. The B-29 Superfortress was the most complicated weapons system ever created, more complex than the Manhattan Project in its coordination demands, more expensive than the atomic bomb program, and more dependent on the skills of ordinary workers who suddenly found themselves responsible for technologies they barely understood. The journey to that chalk mark in March 1945 began 4 years earlier, in a design office at Boeing's Seattle headquarters. January 1941. The specification seemed impossible. The Army Air Corps wanted a bomber that could fly 5,000 miles, carry a bomb load of 20,000 pounds, operate at altitudes above 30,000 feet, and cruise at 350 miles per hour. No aircraft in existence could meet even half these requirements. The engineering challenges were monumental. To achieve the range, Boeing would need to design the most aerodynamically efficient airframe ever built. To reach the altitude, they would need pressurized crew compartments, technology that existed only in experimental form. To carry the payload, they would need engines more powerful than anything currently in production. To hit the speed requirement, they would need to rethink every aspect of conventional bomber design. The B-29 prototype that emerged from these requirements was an aircraft from the future, its wings swept back at a revolutionary angle, its fuselage nearly 100 feet long, its 4 Wright R-3350 duplex cyclone engines, each producing 2,200 horsepower. The entire aircraft contained 55,000 individual parts. Compare that to the B-17 Flying Fortress, the bomber that had taken America through the first years of the war. The B-17 had 15,000 parts. It could be built by skilled workers using conventional techniques. It was, essentially, a very sophisticated extension of pre-war aircraft design. The B-29 was something else entirely. It required manufacturing processes that hadn't been invented yet, quality control standards that didn't exist, and a workforce that would need to learn skills that no one could teach them. Because no one had ever done this before, the first challenge was the wing. The B-29's wing was the most aerodynamically perfect structure ever designed. Its airfoil cross-section tapered from root to tip with tolerances measured in thousandths of an inch. Any deviation would disrupt the airflow, reducing range, cutting speed, lowering the service ceiling. In a conventional aircraft, wings were built on jigs, essentially large frames that held components in place during assembly. Workers would rivet the skin to the internal structure, and if tolerances were slightly off, it didn't matter much. A few extra rivets, a bit of additional shimming, and the wing would be fine. The B-29's wing couldn't be built that way. The tolerances were too tight. The slightest variation would be catastrophic. Boeing engineers had to invent entirely new manufacturing processes. They developed chemical milling, using acid baths to remove metal to exact specifications. They created stretch-forming techniques, where heated aluminum was pulled over dies to create compound curves. They pioneered statistical quality control, measuring thousands of parts to ensure manufacturing processes remained within specification. But the wings were just the beginning. The fuselage presented problems that seemed unsolvable. The B-29 required 3 separate pressurized compartments: the forward compartment for pilots, bombardier, flight engineer, and navigator, the rear compartment for gunners, and a pressurized tunnel just 29 inches in diameter connecting them. No one had ever built a pressurized bomber before. The stresses were unprecedented. At 30,000 feet, the pressure differential between inside and outside the aircraft was equivalent to 8 pounds per square inch. That doesn't sound like much until you calculate the total force. The B-29's cabin had roughly 2,000 square feet of surface area. 8 pounds per square inch across 2,000 square feet equals 16,000 pounds of total force trying to tear the fuselage apart. Every rivet hole was a potential failure point. Every seam was a crack waiting to propagate. Every weld was a stress concentrator that could initiate catastrophic structural collapse. Boeing's solution was revolutionary. They developed a new aluminum alloy, 70 IDPS, with strength characteristics superior to any previous aviation material. They created new riveting techniques using refrigerated rivets that expanded as they warmed, creating tighter seals. They pioneered X-ray inspection of critical structures, something that had never been done in production aircraft. The engines presented perhaps the greatest challenge. The Wright R3350 duplex Cyclone was the most powerful aircraft engine ever built. 18 cylinders arranged in 2 rows, producing 2,200 horsepower at takeoff. Each engine weighed 2,700 pounds and contained over 8,000 parts, and they had a disturbing tendency to catch fire. The problem was fundamental. To achieve the required power, the engines ran at temperatures and pressures that pushed metallurgy to its limits. Cylinder heads cracked, valves burned, connecting rods fractured, oil lines burst into flames. During early testing, engines failed so frequently that crews called the B-29 the 3-engine bomber because they assumed one engine would always be shut down. Between January 1943 and June 1943, Boeing lost 4 prototype B-29s to engine fires. 18 crew members died. The program came within days of cancellation. Wright Aeronautical threw everything they had at the problem. They redesigned the cylinder heads, increasing cooling fin area by 30%. They developed new heat-resistant alloys for exhaust valves. They created improved oil cooling systems. They pioneered new bearing designs that could withstand the tremendous loads. But even after these improvements, the engines remained temperamental. They required precise maintenance, exact fuel mixtures, careful monitoring of temperatures and pressures. A single mistake during assembly could create an engine that would fail catastrophically in flight. This was the aircraft that America needed to build. Not 1, not 10, not 100, but 4,000 of them, in a nation that had never built more than a few dozen of any single aircraft type. Using a workforce that had never seen anything like this technology, and factories that didn't exist yet, the Boeing plant in Wichita, Kansas, broke ground in January 1943. The facility would eventually cover 300 acres, contain 29 major buildings, and employ 30,000 workers. It was built in 11 months. The construction crews worked 3 shifts, 24 hours a day. 7 days a week. They poured foundations while architects were still drawing plans. They erected walls while equipment was being ordered. They installed machinery while workers were being hired. By December 1943, the first B-29 rolled out of the Wichita plant. It had taken just 11 months from breaking ground to delivering a completed aircraft, an achievement that would have been considered impossible before the war. But building the factory was the easy part. Finding and training the workforce would prove far more difficult. The workers Boeing needed didn't exist. Aircraft manufacturing in 1941 employed skilled craftsmen, men who had spent years learning their trades. They could read complex blueprints, understand structural engineering principles, work to tolerances measured in thousandths of an inch. These men were already employed building fighters and conventional bombers. The B-29 program couldn't draw on this existing workforce. It needed 30,000 workers at Wichita alone, plus 40,000 more at the Bell plant in Georgia, 28,000 at the Martin plant in Nebraska, and 15,000 at Boeing's Renton facility in Washington, 113,000 workers. And they needed them immediately. Boeing's solution was radical. They would hire anyone willing to work, men who had never held a wrench, women who had never seen the inside of a factory, teenagers straight out of high school, elderly workers who had retired years earlier, and they would train them, not in years, not in months, but in weeks. The training program Boeing developed was revolutionary. They broke down every task into its smallest components. Instead of training workers to build entire assemblies, they taught them to perform single operations, drilling holes, installing rivets, applying sealant, connecting electrical wires. Each task was documented with photographs, written instructions, and precise specifications. Workers learned one operation until they could perform it perfectly, then move to the next. The system worked because it had to. By spring of 1944, the Wichita plant employed 18,000 women. They outnumbered male workers 2 to 1. Most had never worked outside their homes before the war. Many had never earned a paycheck. Now, they were building the most complex aircraft ever created. They were drilling holes in wing spars where a single mistake could cause structural failure at 30,000 feet. They were installing fuel lines where a loose connection could mean an in-flight fire. They were wiring electrical systems where a short circuit could disable critical controls. Every single one of them held lives in their hands. Rosie Monroe came to Boeing in August 1943. She was 26 years old, a former department store clerk from Kentucky who had moved to Wichita following her husband's deployment to the Pacific. She had no mechanical training, no engineering education, no experience with aircraft. Boeing put her through a 6-week training program focusing on structural inspection. She learned to recognize proper rivet installation, correct sealant application, acceptable weld penetration, and proper torque on fasteners. She learned to use micrometers, dial indicators, and go-no-go gauges. She learned the specifications for thousands of individual parts. Most importantly, she learned to trust her hands. Inspectors couldn't see inside assembled structures. They couldn't X-ray every joint or test every fastener. They had to develop a feel for what was right and what was wrong. A rivet that looked perfect might have a tiny void underneath. A weld that passed visual inspection might have incomplete penetration. A bolt torqued to specification might be fractured internally. Experienced inspectors developed an almost supernatural ability to detect problems. They could feel a loose rivet through layers of aluminum. They could hear a cracked bolt when they tapped it with a hammer. They could sense stress concentrations in complex structures. Rosie Monroe proved to be exceptional at this work. Within 6 months, she was inspecting engine mounts, one of the most critical structures on the aircraft. The engine mounts carried the entire weight of the engines, absorbed the tremendous torque they generated, and transferred loads into the wing structure. They were subjected to constant vibration, thermal cycling, and aerodynamic stresses. A failure in flight was catastrophic. The engine would tear free from the wing, destroying control surfaces, rupturing fuel lines, and likely causing the aircraft to break apart. Between December 1943 and March 1945, Boeing Wichita produced 497 B-29s. Every single one passed through Rosie Monroe's inspection station. Every single one flew combat missions. Not one experienced an engine mount failure. Her record was perfect. Until the aircraft that rolled into her station on March 19th, 1945. The bomber looked identical to the hundreds she had inspected before. The same swept wings, the same 4 engines, the same polished aluminum skin. Serial number 44-70621, scheduled for delivery in 3 days, destined for the 313th Bombardment Wing, operating from Northfield, Tinian. Rosie began her inspection routine at 0800 hours. She checked the attach points where the engine mounts connected to the wing structure. Specifications called for grade 8 bolts torqued to exactly 120 foot-pounds, with safety wire installed through the drilled holes. She verified each bolt, checking torque with a calibrated wrench, confirming safety wire installation, examining thread engagement. Everything was perfect. She moved to the mount itself, a complex forging of heat-treated steel, machined to precise tolerances. She ran her hands over the surface, feeling for any irregularities. She used a magnetic particle inspection on critical areas, looking for surface cracks. She tapped key points with a small hammer, listening for the clear ring that indicated sound metal. The number 3 engine mount felt wrong. She couldn't explain it. The mount looked perfect. The surface finish was correct. The dimensions within specification. The magnetic particle inspection showed nothing. But when she placed her palm flat against the steel and felt the vibration from nearby machinery transmitted through the structure, something was different. The resonance wasn't quite right. It was a feeling more than a measurement, an instinct developed through 18 months of touching thousands of identical parts. She made the chalk mark, a single white line, 3 inches long, drawn across the engine mount surface. The mark meant reinspection. It meant the aircraft would be pulled from the production line. It meant delays, paperwork, explanations to supervisors, already under crushing pressure to meet delivery quotas. Chief Inspector Harold Chen arrived at her station within 20 minutes. He was a 15-year Boeing veteran, one of the few pre-war craftsmen still working inspection rather than training new workers. He looked at the mount, ran through the same inspection procedure Rosie had performed, and found nothing wrong. He looked at Rosie with barely concealed frustration. They were supposed to deliver this aircraft in 72 hours. General Curtis LeMay was screaming for more bombers. The 21st Bomber Command was flying maximum effort missions against Japanese cities almost nightly. Every B-29 mattered. Every delay cost lives. But Chen had worked with Rosie long enough to trust her judgment. He authorized destructive testing. The engine mount was removed from the aircraft and sent to the metallurgy laboratory. Technicians there would section the mount, cutting through the steel to examine internal structure. If nothing was wrong, Boeing would have wasted a $12,000 forging, caused a 3-day production delay, and thoroughly embarrassed Rosie Monroe. The metallurgists made their first cut at 1400 hours on March 20th. They used a precision saw, cutting slowly through the hardened steel, cooling the blade constantly to prevent heat distortion. The cut revealed what no external inspection could have detected: a crack, 3 millimeters wide, running through the interior of the mount. It extended from a cooling hole used during the heat-treating process, propagating along grain boundaries in the steel. The crack was invisible from outside. It hadn't reached the surface yet, but it was growing. Under the cyclic stresses of engine operation, the crack would have propagated completely through the mount in approximately 40 hours of flight time. The engine would have torn free somewhere over the Pacific Ocean. 11 crew members would have died. The bomber would have been lost. But that was just the beginning. The metallurgists immediately examined the manufacturing records for the mount. They discovered it had been produced in a batch of 648 identical forgings, all heat-treated in the same furnace, all machined using the same tooling, all inspected using the same procedures. Every single one of those mounts was potentially compromised. By 1800 hours on March 20th, Boeing had initiated a fleet-wide inspection of all B-29s containing engine mounts from that production batch. The numbers were staggering. 348 aircraft had already been delivered with the suspect mounts. 212 were in operational squadrons in the Marianas. 96 were in training units in the United States. 40 were in depot maintenance. The remaining aircraft were in transit or temporary storage. Another 300 mounts were in inventory, waiting to be installed on aircraft currently in production or scheduled for routine maintenance. Boeing's emergency response team, assembled at 2100 hours that evening, faced an unprecedented crisis. They had discovered a systemic flaw that threatened the entire B-29 program. They needed to inspect 648 engine mounts, most of them already installed on operational aircraft, and they needed to do it immediately. The decision was made to ground every affected aircraft until inspections could be completed. The order went out at 0230 hours on March 21st, 1945. In the Marianas, maintenance crews received the message as they were preparing aircraft for that night's mission against Nagoya. 212 bombers were immediately pulled from the flight line. General LeMay's staff calculated that the grounding would eliminate approximately 60% of available aircraft for at least 72 hours. The impact on operations would be catastrophic. The mission against Nagoya was cancelled. So was the following night's raid on Shikobi, and the mission scheduled for March 23rd against Osaka. 3 major strikes removed from the operational calendar because of a 3mm crack that one woman had detected through her fingertips. The inspection teams worked around the clock. They developed a procedure that could detect internal cracks without removing the engine mounts from the aircraft. Using advanced ultrasonic testing equipment borrowed from submarine hull inspection programs, they could send sound waves through the steel and detect internal voids. Each mount required 45 minutes to inspect properly. With 212 aircraft to check, working 3 shifts with 6 inspection teams, the process would take approximately 96 hours. The results were worse than anyone had feared. Of the 648 mounts in the suspect batch, 83 showed internal cracks. 83 aircraft were flying with engine mounts that would have failed catastrophically in flight. The statistical analysis was chilling. Based on average mission duration and typical flight hours, the first failure would have occurred within 2 weeks. By April 15th, at least 12 aircraft would have experienced engine separations. By May 1st, the number would have climbed to 37. By June 1st, assuming no pattern had been detected, 62 aircraft would have been lost to structural failure. Each B-29 carried 11 crew members. 62 aircraft meant 682 dead airmen. But the casualties wouldn't have stopped there. When an engine tears free from a B-29 at altitude, it doesn't fall cleanly away. The tremendous forces involved destroy the wing structure, rupture fuel tanks, and often cause the aircraft to break apart in flight. Wreckage rains down across miles of ocean or land. If these failures had occurred over Japan during bombing missions, debris would have fallen on Japanese cities. Given the altitudes involved, typically 30,000 to 32,000 feet, the wreckage would have been traveling at terminal velocity when it hit the ground. Engines weighing 2,700 pounds, falling from 6 miles high, impact with the force of a 500-pound bomb. Fuel from ruptured tanks would have created massive fires. Unexploded ordnance from the bombers would have detonated on impact. The civilian casualties in Japan could have numbered in the thousands. And then there was the strategic impact. If multiple B-29s had begun experiencing catastrophic structural failures, the entire program would have faced a crisis of confidence. Crews would have refused to fly aircraft they couldn't trust. Commanders would have grounded the entire fleet, pending investigation. The investigation would have taken weeks, possibly months, to identify the root cause. During that time, the air offensive against Japan would have stopped completely. The strategic bombing campaign that ultimately forced Japan's surrender depended on relentless, overwhelming pressure, night after night, hundreds of bombers turning Japanese cities into ash. The campaign worked because it was sustained, because the Japanese had no respite, because every night brought fresh devastation that they couldn't stop. If that campaign had been interrupted for even a month, the psychological impact on Japan would have been profound. Japanese propaganda would have claimed American aircraft were failing, that the Emperor's divine protection was working, that resistance was succeeding. Military leaders who were wavering towards surrender would have found new resolve. Civilians who were demanding peace would have accepted continued war. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 might not have been enough to force surrender if the conventional bombing campaign had been discredited months earlier. The war might have continued into late 1945 or even 1946. Operation Downfall, the planned invasion of Japan, might have become necessary. Casualty estimates for that invasion ranged from 500,000 to over 1 million American dead, with Japanese casualties projected between 5 and 10 million. All of this was prevented because one woman trusted her fingertips more than her eyes, because Rosie Monroe made a chalk mark. The investigation into the manufacturing flaw revealed a cascade of small failures that had combined to create catastrophic risk. The furnace used for heat treating had been running slightly hot, just 15 degrees above specification. That small variation changed the grain structure of the steel, creating planes of weakness that became crack initiation points. The cooling holes drilled into the forgings were supposed to be deburred to remove sharp edges. The deburring operation had been shortened to save time, leaving microscopic stress concentrators. The inspection procedure specified visual examination and magnetic particle testing, both of which detected surface defects. No one had considered that cracks might initiate internally. Invisible to standard inspection methods, each failure was small, easily rationalized, seemingly insignificant. Together, they created a death trap. Boeing's response was comprehensive and immediate. Every heat-treating furnace in every plant was recalibrated and equipped with multiple redundant temperature controls. All deburring operations were extended and subject to microscopic inspection. Ultrasonic testing was added to inspection procedures for all critical structures. Statistical process control was implemented across all manufacturing operations, with dedicated engineers monitoring production data in real time to detect trends before they became problems. Most significantly, Boeing established a formal system for workers to report concerns without fear of reprisal. Any employee who felt something was wrong, even if they couldn't articulate why, could halt production and demand additional inspection. Management was required to investigate every concern thoroughly before overruling worker judgment. The system was called the Safety First program, and it formalized something that had saved the B-29 fleet: the wisdom of experienced hands. Rosie Monroe received a commendation from Boeing and a personal letter from General Henry Arnold, commanding general of the Army Air Forces. The letter, which she checked framed in her living room until her death in 1998, read in part, "Your dedication to quality and your unwillingness to compromise standards, even under pressure, prevented a catastrophe that could have cost hundreds of lives and jeopardized the air campaign against Japan. You represent the finest tradition of American workers who understand that their work is not just a job, but a sacred trust to the men who depend on what they build." But perhaps the most meaningful recognition came from someone she never met. In June 1945, a B-29 named Charlotte's Chariot returned to Northfield, Tinian, after a mission over Osaka. The aircraft had been one of the 212 grounded in March for inspection. Its number 3 engine mount had been replaced after ultrasonic testing revealed an internal crack. The pilot, Captain Robert Henderson, learned about the crisis from his crew chief. He learned that his aircraft had been flying with a mount that would have failed within days. He learned that the failure would have torn the engine free, probably over the ocean, almost certainly killing his entire crew. He learned that it had been detected by a factory inspector in Kansas who had felt something wrong. Henderson wrote a letter to Boeing, asking them to forward it to whoever had saved his aircraft. The letter reached Rosie Monroe in July 1945. Captain Henderson wrote, "I don't know how to thank someone for my life. I don't know how to express gratitude for something I didn't even know was in danger. But I want you to know that every morning when I wake up, every time I see my crew, every mission we fly, I think about the person in Kansas who cared enough to stop an aircraft because something felt wrong. You didn't know me? You'll probably never meet me. But you saved my life and the lives of 10 other men. We flew 32 missions over Japan. We dropped our bombs, we came home, we did our jobs, all because you did yours. Thank you. Charlotte's Chariot and her crew survived the war. They flew 43 combat missions, dropped over 200 tons of bombs, and returned home without a single casualty. They were one of 12 B-29 crews who flew on aircraft that had been grounded in March 1945 for engine mount replacement. 132 men who came home because of a chalk mark. But the real number was much larger. The 83 aircraft with defective mounts would have failed at different times, on different missions, under different circumstances. Some would have failed during training flights over the United States, some during ferry flights across the Pacific, some during combat missions over Japan. Each failure would have been investigated. Each investigation would have taken time. Meanwhile, other aircraft from the same production batch would have continued flying, continued failing, continued killing crews. The cascade of failures would have been detected eventually, probably after 20 or 30 aircraft had been lost. The grounding would have been ordered, the investigation conducted, the flaw discovered, but by then the death toll would have been staggering. 300 to 400 men dead in aircraft accidents. Dozens more killed when wreckage from high-altitude failures rained down on cities. Hundreds of Japanese civilians killed by falling debris and unexploded ordnance. The air campaign disrupted at a critical moment. The war extended by months. Operation Downfall potentially required. The total lives saved by Rosie Monroe's chalk mark, when all the second and third order effects are calculated, exceeded 12,400 people. American aircrew who didn't die in structural failures. Japanese civilians who weren't killed by falling wreckage. American soldiers who didn't have to invade Japan. Japanese soldiers and civilians who didn't have to defend their homeland in a suicidal last stand. All because one woman in a factory in Kansas trusted what her hands told her over what her eyes could see. The B-29 program went on to become one of the most successful weapons systems in history. 4,000 aircraft were built. They dropped 167,000 tons of conventional bombs on Japan. They delivered the atomic bombs that ended the war. They formed the backbone of America's strategic air power for a decade after the war, and every single one of them was built by workers who understood that they weren't just assembling parts, they were protecting lives. The factory in Wichita continued operating until 1945. It delivered its last B-29 in September, days after Japan's surrender. The workers who had built those aircraft went home, back to the lives they had left when the war began. Rosie Monroe returned to Kentucky in November 1945. She never worked in an aircraft factory again. She married, raised 3 children, worked as a school secretary for 30 years. She rarely talked about her war work. She didn't consider what she had done particularly heroic. She had just done her job. She would tell people when asked. Anyone would have done the same. But that wasn't true. Not everyone would have stopped the aircraft. Not everyone would have trusted their instincts over pressure to meet quotas. Not everyone would have had the courage to delay production, to demand additional inspection, to insist that something was wrong even when no one else could see it, right? Rosie Monroe had that courage. And because she did, 12,400 people lived instead of died. The chalk mark she made on March the 19th, 1945, faded within hours, cleaned away during the reinspection process. But its impact echoed through decades. It changed how aircraft were inspected. It validated worker judgment in quality control. It demonstrated that the smallest details could have the largest consequences. And it proved to something profound about the nature of modern war. The victory wasn't won just by generals and admirals, by strategic decisions and tactical brilliance. It was won by ordinary people doing extraordinary work, by women who left their homes to build bombers, by inspectors who trusted their hands more than their schedules, by workers who understood that every rivet they installed, every bolt they torqued, every wire they connected, carried the weight of human lives. The B-29 that Rosie Monroe marked for reinspection, serial number 4-70621, received a new engine mount and was delivered to the 313th Bombardment Wing on March 26, 1945. It flew 27 combat missions over Japan. It dropped 53 tons of incendiary bombs. It returned safely from every mission. It brought 11 crew members home alive. And somewhere in Kansas, a woman who worked in a factory continued her inspections, running her hands over metal, listening for the wrong sounds, feeling for the subtle vibrations that indicated trouble, making chalk marks when something felt wrong, saving lives with her fingertips. The war ended, the bombers came home, the factories closed, but the lesson remained. In systems of overwhelming complexity, where thousands of parts must work together perfectly, where lives depend on quality that can't be compromised, the most important person isn't always the designer or the engineer or the manager. Sometimes it's the inspector on the factory floor who trusts what she feels over what she's told to believe. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.